Okay, so I'll get started here just with a quick word about the quiz because I've had a few questions and there seems to have been a little bit of confusion with some of you. So I apologize if I didn't communicate all this information clearly. Each Thursday after class, I am going to post a quiz to D2L. So if you open the D2L page for this class, then if you go to the heading activities and then under that menu click on assignments, you will find the quizzes there. So at the moment, last week's quiz is up. And if for some reason you did not take last week's quiz on Thursday, I have opened access up again for the next 24 hours. So you can take that quiz within the next 24 hours and upload it as well. And then the new quiz from today will be online in the same place by 3:30. And again, you will have a 24-hour window. In that 24-hour window, when you click on the quiz, you have 1 hour to complete it and get your solutions uploaded back to D2L. So please reach out to me today if you are still uncertain about any aspect of this, so that you don't fall behind in terms of having to complete these quizzes. Does anyone at the moment have a question about quizzes? I'll give you a minute or so if you want to ask or type the question into chat. So I have a question asking when the quiz is due. The quiz that I post today, and I guess this now applies to the one from last week if you didn't do it, the quiz will be due by tomorrow at 4 p.m. You have 24 hours starting at 3:30 today that you can click on the quiz to take it. This opens a file. You'll take the quiz on paper or on your tablet if you're writing on a tablet. And whatever you write, from when you click on the quiz, you have 1 hour to finish that work and upload back to D2L. So 24 hours at any point during that time you can start. Once you click on it, you have 1 hour to get it completed.
Is there a timer or something that we can see, like how much time we have left when we're taking?
No, there's unfortunately no way to run a timer like that. And I'm not going to be overly strict. Like if I see that you submitted 2 minutes over the 1 hour mark, like, I'm not going to penalize you. You'll be able to upload the file still. So you just want to make sure like you're not taking 3 hours from when you access the quiz before you upload it. But I'll be reasonable with that time allotment. Then also someone has a question about grades. I'm working on getting all the grades integrated into D2L. That's probably something I'll manage to get done over the weekend. So going into next week, hopefully all the grades will be centralized in D2L that you can see quiz grades, homework grades, etc. At the end of the session today, we'll also spend a little bit of time talking about the test because there is a test next week, but let's work on our examples first. So I'm switching over to the worksheet. And so the problems we're doing today helps round out chapter 13. So we're wrapping up chapter 13 with these examples today. First problem looks at a mechanic who runs diagnostic tests on 168 new cars and finds that 11 of them are affected by electrical problems. And we are asked to calculate the margin of error. Now, remember here that the margin of error is defined as Z star times the standard error. And to calculate standard error, you need to take the square root of p hat times q hat over n. So to do this calculation, you need to know both the value of z star and you need to know the value of p hat. P hat is your sample proportion and z star comes from the confidence level. So in this case, p hat is the proportion of successes in our sample, which means it's the 11, successful tests in this case means tests that showed an electrical problem, but those 11 tests out of the 168, and as a proportion, that's 0.065 or 6.5%. And our Z star value, if you're doing 90% confidence, then your Z star value is 1.64. So we can now calculate our standard error. That's going to be the square root of 0.065. And then remember the Q hat value is 1 minus the P hat value. So 1 minus the 0.065 gives us 0.935. And our sample size is 168. If we do this whole calculation, we're going to find 0.019 or 1.9%. So that's our standard error. Margin of error is now going to be 1.64 times the 1.9%. And if you do that calculation, you'll get a margin of error of 3.12%. Now, part B starts by providing us with a margin of error. It says the margin of error in a specific calculation is 5.7%, and we want to know what was the confidence level that resulted in this calculation. So our base formula is still margin of error is Z star times standard error. Which value tells us what our confidence level is? That's the Z star value. So if you're trying to determine the confidence level, you are effectively trying to find Z star, because then you can interpret the Z star value to find the confidence level. So in this case, we know the margin of error is 5.7%, and it's still the same standard error we had earlier, 1.9%, because the success proportion didn't change, the sample size didn't change. So to solve for Z star, I'm just going to divide by the 1.9% on either side, and that gives me a Z star value of 3. So the question now is, what confidence level is associated with this? Well, remember the Z star value tells you how many standard errors you go in either direction from the center of the distribution. So if Z star is 3, that's asking us what proportion of values lie between -3 and +3 on our bell curve. And when have you seen a Z value or a Z star value of 3? Well, that's connected to the 68, 95, 99.7% rule, right? A Z value of 3 means it's a 99.7% confidence level. You could also do this with a normal table. You could look up z equal to 3 in a normal table if you were unsure, like if you just saw the value 3 and you didn't remember that's associated with 99.7%. But if you look it up in the normal table, you have to remember that means what you're looking up is total area to the left. In fact, let me open up the normal table here and show you that really quickly. So if I were looking up in my normal table a z-value of 3, I would get 0.99865. Now, what that tells me is, I'm looking up 3, and this is now telling me the total area to the left, or the total proportion of values to the left is 0.998, what was that, 99865. Which means the value to the right, if I know in total the proportion is 1, so I subtract from 1 the 0.99865, that gives me 0.00135. Now, I need to know, again, what the area is between -3 and +3, but by that symmetry of the normal distribution, I now know the area on the right is 0.00135, but the area on the left has to be exactly the same. So what's in the middle here is 1 minus 0.00135 and subtract another 0.00135. And that gives me 0.997 or 99.7%. So this is definitely a more tedious way of doing it. I think it's helpful to have the important z-values noted down or memorized. But this is how you could do it from scratch with the normal table. And then let's look at part C of this problem. Part C says, it's generally believed that electrical problems affect about 14% of new cars. Construct a 95% confidence interval and comment on whether the data is consistent with this belief. Now, 95% confidence interval means the z-star value we use is 2. And the formula for our confidence interval is p hat plus or minus z-star times the standard error. Now, we already know the value of p hat, that's 6.5%. The z-star is 2, and we'd calculated our standard error, that was 1.9%. So our confidence interval in this instance ranges from 2.7% to 10.3%. And that's now what we want to base our conclusion on. Given this interval, is 14% a reasonable value? And I would say no, 14% does not appear to be a reasonable value. It's specifically we would emphasize at 95% confidence, because at the 95% level, it's not inside the confidence interval. So yes, is it possible that it could be the true value? Of course, but 5% chance of it being the value, 95% chance that it's not, because the 95% interval covers 95% of the possible values. So given the interval, 14% does not appear to be a reasonable number. So if anyone has questions specifically about problem number 1, any part, A, B, or C, you're welcome to ask now. I'll wait a little bit if you have questions. Okay, let's move on to problem number 2. A researcher interviews 225 randomly sampled TCU students and finds that 97 of them prefer Android phones over iPhones. Calculate the margin of error for a 99% confidence interval for this quantity. So margin of error is Z star times standard error. For a 99% interval, Z star is going to be 2.54. And we need P hat to calculate our standard error. So that's the success proportion. And no, I'm not saying people with Android phones are more successful than people with iPhones. I am an iPhone user. But in this experiment, having an Android phone is our definition of a successful outcome. So this is the proportion of successes. And if you calculate that, you are going to find a proportion of 0.431 or 43.1%. Now we can calculate our standard error, square root of P hat Q hat divided by N. So the 0.431, 1 minus P hat gives us a Q hat of 0.569, and our sample size is 225. If we take the square root of that, we get 0.033 or 3.3%. So we can calculate our margin of error now. Our margin of error is 2.54 times the standard error of 3.3%. And so that gives us a margin of error of 8.4%. Now, I made a slight correction to this problem, the version I posted on D2L. So in part B, someone calculates a margin of error of 6.6%. And we want to know what the confidence level associated with that is. So same calculation or same base formula. If we want confidence level, that's equivalent to finding Z star. So in this case, our margin of error is 6.6%. Our standard error is 3.3%. So what we end up with for Z star is a value of 2. And a Z star value of 2 gives us what confidence level? Well, That means we have a confidence level of 95%. And again, you could go and do this with the normal table, but I recommend just having the important z-values noted down. And if you end up really close to one of them even, like if this had been 1.99 or 2.05, if it was just pretty close to 2, then I would still accept 95% as an answer. Any questions about margin of error calculations? We're about to move on to something else. I'll give you an opportunity to ask about margin of error. Okay, problem number 3. Now we're moving on to sample size calculations. So a researcher wants to determine what percentage of products manufactured by a company are defective. The testing process is destructive, and what that means is if you, in this case, test if a product is defective, the only way to test is to destroy the product. So clearly in a situation where your test is destructive, you want the smallest sample size possible to reach your conclusion because you don't want to destroy thousands and thousands of products to test them. So this researcher, she wants to figure out what sample size to use so that a 2% margin of error is obtained at a 95% confidence level. So we are given a margin of error of 2% or 0.02. For sample size calculations, it's important to express this as a decimal. And for 95% confidence, we know our z-star value is 2. And we are being asked here for the most conservative estimate of sample size. So you have 2 sample size formulas. One of them is called the most conservative, and then the other one uses p hat. So for most conservative, the formula for sample size n is 0.25 times z-star divided by margin of error squared. So in this case, 0.25, and then our z-star value is 2, our margin of error value is 0.02, and that quantity we need to square. So this is 0.25 times 100 squared. And so if you do this calculation, you get a sample size of 2,500. In this case, it's exactly an integer. If it's not an integer, you have to round up to the next value. So that's our most conservative estimate of sample size. Part B now says the researcher runs a small pilot study and finds that 2 out of 35 products are defective. So that gives us a way of estimating p hat. In our sample of 35, we found 2 defective items, and expressing that as a proportion 2 divided by 35 is 0.057. We are still going to use z-star equal to 2 because we're still doing this at the 95% level, and we're still trying to obtain a margin of error of 0.02, but we don't have to go the most conservative route because we have some idea of what the true, we have an estimate of the true proportion. So in this case, the sample size is calculated as p hat q hat times z-star over me squared. So this will be 0.057. Q hat is 1 minus 0.057. That's 0.943. And then we still have 2 divided by 0.02 squared. If you go and do this whole calculation, you'll get 537.5. And so since there's a decimal part, we round up to 538. And I want to emphasize here how much we have gained by the researcher doing the pilot study. Like in the absence of any other information, she would have to go and collect 2,500 observations, or in this case, destroy 2,500 products to test them. But by doing a little bit of a pre-study, like just testing an initial 35, she can figure out that she'll probably be within the margin of error if she just in total tests 538. So that is a massive reduction in resources needed, which illustrates the power of doing something like a pilot study to get an initial sense of what's going on in the data. Anyone have a question about problem number 3? We do have another example looking at sample size. So let's jump into that one. A researcher wants to determine how many people to interview for an opinion poll. Since resources are limited, it's important to determine the best sample size so that a 1.2% margin of error is obtained at the 99% level. So again, we want to start by calculating our most conservative estimate of sample size. Most conservative estimate is 0.25 times Z star over margin of error. And what we know for 99% level, our Z star is 2.54, and our margin of error as a decimal, 1.2%, is the same as 0.012. We want to square that second quantity, that ratio. So if you do this calculation, you'll find here 11,200.7, round up to the next integer. Most conservative estimate says go and interview like 11,201 people for this opinion poll. Like that's a lot of people to interview. But the research company does a small pilot study, and they, in their pilot study, find 22 of 80 people are successes. So that gives us a way of estimating the success probability. So 22 divided by 80 as a proportion is 0.275. Now we can use the more accurate sample size formula because it uses more information. The Z star and the margin of error values don't change, but we can now use the p hat value. So we'll still have 2.54 divided by 0.012 squared. But in this case, I get 8,932.6, round up to the next integer, 8,933. So that's still a pretty big sample size, but it does represent a reduction of more than 2,000 people. So more than 2,000 fewer interviews that have to be done to complete this opinion poll project. So it's a lot, but having a little bit of pre-information does help you achieve better results.